star, so due to the emission of radiation, the neutron star gradually spins down. So now if the observer measures the timing, it just times the time that the pulses arrive to Earth, they can measure both P, the period of the pulsar. So this is given by the intervals between the pulses, but they can also measure P dot. They can measure how gradually, very slowly over time, the interval between the pulses gets slightly longer. So the clock ticks slightly slower as the pulsar spins down. And actually, it's quite cool.
There's a question?
Yes.
Yeah, I have a question. What happens to the magnetic field itself? Can it decay as well?
Yes, so magnetic fields can in principle change, but they don't seem to, I mean, we think that they don't change a lot on the time scales that I'm going to talk about, because I'm going to talk about old pulsars that are giga years old, but sometimes people do talk about these glitches once in a while. There's some deformation in the neutron star as it spins down more slowly at some point, and you get kind of like a quake that changes the configuration. That can get to a glitch in the magnetic field.
I'm not talking about glitches. You're talking about the periodicity of 10 to the 9 years.
Yes.
In which the spin slows down, which is good. But during this period, doesn't the magnetic field also changes its amplitude?
Not a lot, I think, no. Because the neutron star basically remains, it has more or less the same, it has the same radius, it has the same mass, so.
Well, but you're losing energy. So what part of this energy is magnetic energy?
Well, you're losing energy, but I mean, usually magnetic fields change due to, you know, if you suddenly contract and you try to, I don't know, conserve your flux or something like that, then the magnetic field would change. But I don't think it changes a lot. I mean, I think you lose spin energy, but I'm not sure, but I don't think that the magnetic field changes a lot. I think the general story is that the magnetic field remains more or less the same, but your rotation rate is the one that changes. So they don't change on the same time scale.
Well, I think expect some changes because as the spin changes, so are the currents change, right? You need the currents to maintain the magnetic field, right? With the spin. Okay, never mind. Just okay.
No, I'm trying to think about this. So usually magnetic fields are generated by some combination of rotation and convection, which provides these currents. So imagine that if
how much convection you have in a neutron star?
So if the pulsar spins down, so if the pulsar cools down significantly at this time, if its temperature changes significantly, then maybe B changes. Anyway, I'm not sure, but as far as I remember, I think B doesn't change that fast. But now that I think about this, if the neutron star cools significantly during this time, then B might change. But yeah, just have to check this.
Okay.
Okay. Anyway, what I was trying to say is that you measure P, and so it's actually quite cool. Just by timing the process, just by measuring P and P dot, using these equations, you can now estimate quite a lot of physical properties of the pulsar. So you can calculate the spin down luminosity. You can calculate you can calculate the instantaneous magnetic field B, even if it changes over time. And you can also estimate an age, P over P dot. This is how long the pulsar has been spinning down this way. And they think that even if B changes, it probably changes at least on this time scale, because this is the time scale on which the properties of the neutron star change. So anyway, you can estimate an age, P over P dot, and the ages for millisecond pulsars are typically several gigayears. Yeah, they don't think it matters too much for the analysis if B also changes on the same time scale or longer. I don't think it should change on a shorter time scale. That's for sure. Okay, and because pulsars are such accurate clocks, there's even more physics you can do, again, just by timing the pulsars. And that's if the pulsar orbits a companion of some mass m, then as you can imagine, if the observer is over here, then the arrival time of the pulse will sometimes change. Sometimes the pulse will arrive a bit early or a bit late. due to this extra distance that light has to travel to the observer. So as you can see, the timing of the pulse will be modulated by the orbital period, PO, so you can easily measure the orbital period. And you can also translate the amplitude of the time delay, the delta t, the amplitude of the modulation, into a distance a semi-major axis, using the speed of light. So now you know both the orbital period and the size of the orbit. So using Newton's laws, you now know the mass of the companion. And more precisely, this time delay is only sensitive to radial motion towards the observer. So if you don't know the inclination of the system I, all you measure is the minimum mass. You only measure m sine I. And because pulsars are such accurate clocks, this method is very precise. You can easily detect companions down to very low masses. And actually, the first exoplanets that were detected around a neutron star, and one of those had a ridiculously low mass. It was more or less the mass of the moon. So you can easily detect very low mass companions using this method. And one such low mass companion was detected in 1988, and that one was called the Black Widow. So what they detected a millisecond pulsar. It was orbited by a low mass companion, a few percent the mass of the sun, 3% the mass of the sun, on an orbit of about 9 hours. And there was another piece of information, and that is the system is eclipsing. So every time the companion comes between us and the pulsar, the radio beam is being eclipsed. It's being blocked. So that was the discovery paper in 1988. And the same year, soon after, came out these two theoretical papers, providing more or less the same explanation, the same picture. And the picture that they suggested was that some fraction of the pulsar's spin-down power, this Larmor radiation, gets transformed into high-energy photons, into gamma rays. These gamma rays hit the companion, and when they hit the companion, they launch a wind. They evaporate part of the companion, and this evaporative wind is the one that causes the eclipses, is the one that blocks the radio beam. So that was the picture they suggested, and this led David Eichler and Amir Levinson to suggest a name for this process or for the system. They called it the Black Widow. And kind of the general scenario that led to this name was that how do you end up with this low mass companion on the first place? So the idea was that you start from a regular main sequence star that somehow gets into Roche-Lobe contact with a neutron star, and through Roche-Lobe overflow, it transfers material to the neutron star. This transfer of material spins up the neutron star. So this is how you bring neutron stars to millisecond periods. And then later on, the pulsar uses its newly acquired rotational energy to evaporate what's left of the companion. So this is how you transform a main sequence star, roughly one solar mass star, into this much lower mass companion. And this scenario led the authors to resemble to the authors to the Black Widow spider that devours its companion soon after mating. And as you can see, I've been able to find these very similar pictures online. And actually, this paper kind of reminds me of how Fred Hoyle coined the name the Big Bang for the Big Bang theory. So as you probably know, Fred Hoyle, well, he was a critic. He was against the Big Bang theory. He had another theory in mind. And the Big Bang name was allegedly was supposed to carry some negative meaning. So this paper too kind of criticizes this whole scenario, but this was still the paper that coined the catchy name that we use today. So that was 1988. Then we had only one system.
So,
yes,
we see the millisecond pulsar, so presumably the radio is angled towards us, and it's eclipsing, so it's also all in the same plane and all towards us, at least occasionally.
Yeah, so actually it's, so there is some beaming, but I think we're not really sure of the beaming, we're not really sure how beamed is the radio beam, but yes, but it is somewhat beamed because it's a pulsar. well, actually from the light bulbs, you can know how much it's beamed. Yeah, so it's pointing towards us.
Yeah.
So it's a bit more tricky than that, right? So the pulsar just keeps rotating like a lighthouse, right? So it doesn't have to be. It actually, if it were completely aligned with the orbit, right? It doesn't have to be aligned with the orbit. Even if it's not aligned with the orbit, you will still see.
Is it periodically aligned with the direction to us, and the eclipse means that the axis also, the plane also has to be aligned somewhat towards us. So at least occasionally, I guess it would have to be either beamed or lensed.
I don't think there's lensing, but so if the observer is over here, no, so yes, so the thing is that so as we'll see, the thing is that the companion is fairly large, so it kind of feels its source lobe, and it's very close to the, well, it feels a relatively large angle because it feels its source lobe, so it doesn't have to be perfectly aligned to be eclipsed. I mean, it can't be in any random direction, but because the Roche lobe, which you feel kind of covers a relatively large angle of the sky, you don't have to be exactly aligned for the eclipse to happen. So what I'm trying to say, and maybe that was your question, is that the fact that you're eclipsing doesn't really give you I. You still have this degeneracy that you don't know sin I.
I have another question. What about diffraction? Could you see diffraction in this object?
Diffraction?
Yeah.
Of what?
Radio waves, yeah, they should be able to bypass this obstacle, right? So you might be able to...
I'm not sure. I mean, you will still have, well, they have, so radio waves do have a large wavelength of meters, but the kind of the size here is still much larger than meters. So I think it's still largely optical geometry, right?
Well, not here, but if it goes through some wind that was ejected by this companion, as is being plotted there,
then you have some plasma effects, right?
You might be able to see. I don't know if it was seen or not, right? Because I'm not familiar with this object in detail. So I'm just wondering if it was seen some sort of a diffraction, which could tell you about the properties of the wind, actually.
Yes, so not that familiar with the properties of the radio beam. So for me, the radio, so as you see, the data that I'll use from the radio observations will be mostly the timing, and that's it. So I'm actually not that sure about the information in the radio beam except for timing. I mean, I'm sure there's some information. I mean, I'm sure you can tell something about the interaction, but I think you can't tell a lot because as far as I know, the radio observers can't really tell anything about the density of the wind, for example, from the radio beam. So I'm sure there are some non-trivial effects, but I'm not fully aware of them. And as far as I know, you can't really deduce any useful properties of the wind from the radio eclipses, maybe except for some trivial limit that the wind has to have some minimal density and ionization probably. That's my guess.
Mm-hmm.
Okay, so yeah, so that was 1988. We had one system, we had the Black Widow. But in the last decade, we've actually discovered a whole bunch of rather similar systems. So these are all millisecond pulsars, all with low mass companions, typically a few percent the mass of the sun, on all orbits of several hours. But you can see in the right column that they do have somewhat different pulsar spin-down powers, and I'll talk about this later. So now we call this whole class of objects Black Widows. And what made the discovery of these Black Widows possible in the last decades was two things. So first, these millisecond pulsars are also gamma ray sources. And the Fermi satellite discovered many gamma ray sources, which were then followed up from the ground by radio telescopes. And there was also a designated radio survey at the Parkes telescope in Australia that was designed to detect millisecond pulsars. And many of those millisecond pulsars turned out to be black widows. So now we don't have just one black widow, we have a whole population of black widows that are similar but not exactly the same. And the question that I would like to focus on in this meeting is, can this evaporation scenario that was suggested to explain the original black widow more than 3 decades ago, can it really explain the whole population of newly observed black widows? So that's the question. I'm going to focus on. And to answer it, we'll have to actually calculate how efficient is the wind. So we have a pulsar. It emits some high energy flux F, and this flux hits the companion. And we would like to calculate the mass loss rate m dot from the companion, how much mass is lost in this wind. So this is a fairly well-defined question, and we'll divide the solution into 2 steps. The first step will be to calculate P naught, the wind launching pressure. So this is the pressure level inside the companion from where the wind is being launched. That will be the first step, and given this P naught, the second step will be to actually calculate m dot, the mass loss rate of the wind. So that's what we're going to do for the next few slides. It's a bit tedious. There are some details, so please bear with me. And then after a few slides, we'll get to the answer. Okay, so let's start with the first step. Let's start by calculating the wind launching pressure. So to calculate it, we first need to understand why is there a wind launched at all. So let's assume there's no wind. Let's assume that the companion's atmosphere just reaches equilibrium with this incoming ionizing irradiation. As we can show, we should only be interested in the outer optically thin layers of the companion. So let's calculate this equilibrium of an optically thin gas subject to ionizing irradiation. So this is actually a standard calculation which has been done in several different contexts in astrophysics. It's called the ionization equilibrium. And what you usually do, you write down all the heating and the ionization terms. And since the gas is optically thin, these are linear in both the density of the gas wall and the flux F. And in equilibrium, the heating is balanced by cooling, the ionization is balanced by recombination. And since these two are two-body processes, they depend on rho square, and they're also some function of the temperature of the gas T. So now in equilibrium, you equate the blue terms with the red terms, and then you can find the equilibrium ionization fractions of all the species, and you can also find the equilibrium temperature T, and so the equilibrium pressure P. And because the terms scale like this, you can find kind of a universal solution. You can scale out the magnitude of the flux F, so you can write down the equilibrium pressure divided by F is some function G that we'll have to calculate of the density rho divided by F. And the equilibrium solution typically looks like this. So the y-axis is the scaled pressure, and the x-axis is a scaled density. And the equilibrium solution typically follows this red line, well, these black lines, these dashed black lines are lines of constant temperature. Can everyone see the plot, by the way?
Yeah.
Okay, right. So to give some intuition as to why the equilibrium looks like this, let's start from high densities. At high densities, the flux is unable to ionize the gas. So the gas remains neutral, so it can cool efficiently by hydrogen line cooling, which depends exponentially on the temperature T. And this exponent can keep the temperature at an almost constant 10 to the 4 Kelvin. But as you go to lower and lower densities, at some point, the flux is able to ionize the gas. So now hydrogen line cooling is less efficient. So you heat up to higher and higher temperatures. You go up here, but there's a limit to how hot you can get. So an incoming flux can't heat the gas to a temperature basically higher than itself. So you reached what's called the Compton temperature, which is more or less the mean energy of the incoming photons. Above that, the gas can cool efficiently by inverse Compton scattering. So that's why we transition between these two temperatures, and the transition typically takes this form. And now let's try to actually follow this equilibrium solution inside the atmosphere of the companion. So let's start deep inside the companion's atmosphere, high density, high pressure, and let's go outside the companion. So we're going to lower densities and lower pressures. So we go down here until we reach this point. And this point, we're supposed to go to to lower densities, but to higher pressures. We're supposed to climb uphill, but this is unphysical. This is like the van der Waals loop in the van der Waals gas. It's unstable. So what we do instead, we go along a constant pressure line over here, again, like in the van der Waals gas. And as along this line, you can see that the temperatures keep rising. You go to higher and higher dashed lines until at some point, the temperature is so high that the speed of sound exceeds the escape velocity from the companion. And when this happens, this means that there's no longer a stable hydrostatic solution. The only solutions are hydrodynamical wind. So the wind is launched at this pressure. All these points have the same pressure. So all you have to do, you have to calculate this point over here. And because of this kind of universal scalings, you can see that this wind launching pressure is proportional to F, the incoming flux. And that's what you might intuitively expect. The stronger the irradiation, the deeper from inside the companion you launch the wind. Okay, so that's the wind launching pressure. And now, given the wind launching pressure, it's actually quite a neat and clean hydro calculation to calculate the mass loss rate from the wind. So we simply calculate the hydrodynamics of the wind as it goes out from this P0 into larger and larger radii R outside the companion. So we write down the equation of conservation of mass over here and the momentum over here. And when you combine the two, you get the classical wind equation. So this equation will give you so V is the velocity, the outward velocity of the outflow, of the outgoing wind. And you can see that if you want to calculate the acceleration of the wind as it goes outwards, if you want to calculate dVdr, then the equation has a critical point. You have to divide by this term, 1 minus cs squared over v squared, that goes to 0, changes sign when the flow reaches the speed of sound. So v is the velocity of the flow, and cs is the speed of sound. So when v, the flow velocity, reaches the speed of sound, this goes to 0. So you can see that the only physical solutions, the only solutions that keep accelerating as you go out from the companion are the ones where the right-hand side goes to 0, also changes sign, exactly at the same point where this term goes to 0. So this is called the sonic point. This is the point of the radius where the outflow reaches the speed of sound. And again, you can find it by equating the right-hand term to 0. And the simplest example is one where the wind is isothermal. So if the wind has a constant temperature, you can drop all these dTdr terms, and then you can see that the sonic radius, where this goes to 0, is none other than the familiar Bondi radius. And the reason that the sonic point is interesting is that in many cases, the sonic point is the one that determines the mass loss from the companion. So to give some intuition, basically by definition, up to the sonic point, the flow velocities are subsonic. So if the speed of sound, for example, is below the escape velocity from the companion, it means that the velocities up to the sonic point are much lower than the escape velocity, so the flow is almost hydrostatic. So in this case, you can now use hydrostatic equilibrium to calculate the density up to and at the sonic point. So now you know the density at the sonic point. You also know the velocity at the sonic point. By definition, it's the speed of sound. And you also know the surface area at the sonic point because you know Rs. So now you just multiply all three and you can trivially get m dot, the mass loss rate from the companion. So in many cases, knowing the sonic point quickly allows you to know m dot, the mass loss rate from the companion. So that's why we focus on it.
We have a question?
I have a question, yeah.
Yes.
Yeah. This is a 1D analysis.
Yes.
How does the result changes when you're starting adding, winds which are not necessarily radial, turbulentic wind of whatever, any kind?
Yes, so great questions. So actually, before worrying about turbulence, I would worry about something else. So if you can see my laser cursor, I'm writing these 1D equations, but we've got this object here that kind of ruins the 1D party, right? Because it can change the gravitational field. So I mainly focus about the effect of how the pulsar's gravity field changes the 1D equations. Now about turbulence.
Well, not just turbulence, it's just one example.
Yeah.
Qualitative.
Yeah, so I've never thought about turbulence. So I guess in order for not to have turbulence, you have to check the you have to compare the diffusion to the advection terms, right? You have to check if basically if the viscosity of the gas is large enough to prevent turbulence. And I've actually never checked this for this problem, right? Because there's a number. You can equate basically the viscosity to the momentum terms, and you can change whether the flow is laminar or turbulent, right?
Yeah, it's a Prandtl number that you're looking.
The what?
Prandtl number, it's called.
Yeah, wait, there's another number. I'm just forgot its name. There's also
You're thinking of the
Reynolds, yeah, the Reynolds number, yeah. Oh, but it's also magnetic. Yeah, but it's magnetic, so maybe it's the Prandtl number. Yeah, so I've never actually checked this in this context, so I actually have no idea. Yeah, so the analysis will be 1D with the correction that are introduced in the next slide for the 2D effects due to the gravitational influence of the pulsar. Yeah, I've never thought about turbulence. That's interesting. Yeah, I mean, on average, it will still be 1D. Yeah, I'm not sure what the effects will be. It's a good question. Okay, so what I was saying was that, okay, so we have the sonic point, but the complication in our case is that we can't drop these terms because in our case, the wind is not isothermal. The pulsar keeps heating up the wind, so the temperature keeps changing. So if you want to calculate the sonic point, and if you want to find the velocity profile, you need to know the temperature profile. But the difficulty here is that the temperature profile itself depends on the velocity, because how much time the flow has to flow actually through each radius R, how much time it has to get heated by the pulsar though, depends on the velocity though. So what I'm trying to say is that you have to solve the temperature and the velocity together. You have to solve them combined. And the ones who did this many years ago were Bigerman, McKee, and Shields. So they solved it for a slightly different problem in a different scenario, but you can quite easily adapt the results to our case. And what they showed that this interplay, this competition between the thermal timescale, the heating, and the dynamical timescale, the flow, can be characterized by a single physical quantity, which is called the characteristic temperature. And its definition is very simple. It's simply the temperature that the flow would have reached on a sound crossing time. So explicitly, it's defined by gamma, the heating rate per particle, which depends on the pulsar's flux and on its spectrum. So this is just ergs per second going per particle, and we multiply this ergs per second by a time. And the time is defined as the sound crossing time, R, the radius of the companion, divided by the speed of sound, which itself depends on this temperature. And what they showed that kind of all the equations scale to this quantity. In a way, you can see that this temperature kind of measures the ratio between the thermal and dynamical timescales at the sonic point. So they showed that all the equations just scale to this temperature. So once you calculate it, you can calculate the sonic point, and then you can calculate m dot. And the results look like this schematically. So this is the mass loss rate m dot as a function of this temperature T. And you can see that this temperature basically just measures the strength of the flux F. So it's monotonic in the flux F. So the stronger you heat, the higher this temperature. And the m dot, the mass loss rate, is also monotonic in this temperature. So the stronger you heat, the more mass you get out of the companion, as you might would have expected. And you can see there are different regimes depending on how this temperature compares to, on the one hand, the Wheeler temperature, or the gravitational temperature, the escape temperature from the companion, and on the other hand, the inverse Compton temperature of the incoming radiation. So you can see there are different regimes. I should also say that there's this older solution given by the black line calculated by Ruderman et al. So they kind of ignored all this heating. They assumed for simplicity an isothermal wind. Then you can solve the equations much more simply, and then you get this linear relation. But when you actually calculate the thermodynamics of the wind, you can show that you're always somewhat below the limit. The evaporation is always somewhat less efficient than this simpler limit. And one specific interesting regime is this blue regime, left of TG, which we call the cold regime. So in this regime, the flux is weak. So m dot, the mass loss, is also weak. And therefore, it's being affected, it's being pulled back, it's being slowed down by the gravitational field of the companion. And because of this reason, as I hinted in the previous slide, you can also be affected by the gravitational tidal field of the pulsar. So if the companion feels or almost feels its Roche lobe, then its gravitational field is strongly distorted near the L1 Lagrange point. And then you can show that this significantly affects the structure of the wind. So the solution is actually 2D and not 1D when you feel the tidal field of the pulsar. So actually you have some angular distribution which we solve, and that's why you get these two solutions. One solution for detached companions that are far from feeling the Roche lobe. So this is a 1D solution, and one for companions that are close to feeling the Roche lobe or feel the Roche lobe, and this is a 2D solution. So that's why we get these two sets of solution. Okay, so this is the qualitative picture. And I hope you didn't lose me in the previous few slides, but even if you did, it's not that bad because here we have the final results. So this is the final answer. Given all this calculation, you find a rather simple expression for m dot, for the massless rate from the companion. So this is grams per second going from the companion. And you see that the equation is simple, but now you have to plug in both this P naught, the wind launching pressure, and this characteristic temperature T, which I hope I gave some intuition as to how we calculate those. And when you calculate those, you can then plug them in and you get an expression for m dot. And therefore you have an expression for m over m dot, or the evaporation time. So this is how long it would take the pulsar to significantly evaporate its companion, to bring the companion to say half of its current mass. Okay, so you get this equation. So maybe any questions before I try to apply this equation to the actual observations?
And what's the TCH and TG?
What?
TCH and TG, where are they defined?
Yes, so TG is simply, I didn't define it here, but TG is simply KTG equals to GM mu over R. So this is simply the kind of the escape temperature from the companion. Okay, so that's TG. And TC is a bit more tricky, TCH is a bit more tricky, it's defined over here. So KTCH is the temperature that you would reach if you're being heated by the pulsar. Gamma is the heating rate by the pulsar. And if the time that you have to get heated is the sound crossing time. It's R over the sound speed, where the sound speed itself is the sound speed evaluated at this temperature. So this is why you get this 2/3 power.
Okay.
So kind of TCH over TG kind of measures how hot the wind gets with this heating with respect to the escape velocity from the companion. This is intuitively this ratio. Yeah,
Another question, just to make sure I'm understanding the system. The companion is constantly being evaporated or blown away by the heating of the pulsar. Is
yes.
There also, and it's also always filling the Roche lobe? Is there an accretion disk?
Yes. So that's a good question. Yeah. So in the analysis over here, I started by just assuming that the companion has some radius, but then for this equation, you can see my hand obviously. For this equation over here, what I assume is taking this branch of the solution. So here I try to find the kind of maybe the most optimistic scenario, the strongest wind. So the strongest wind is when the companion has the largest radius. Then it's when it's most susceptible to this evaporation. And the largest radius is when you feel your Roche lobe. So for the analysis from now on, I'm taking kind of the strongest wind you can imagine, which is when you feel your Roche lobe. And I'll show that even then the scenario has some issues. So I'm taking this branch of the solution, you feel your Roche lobe, which I'll talk about more again. And going back to Asaf's question, just to give some intuition, you can see that m dot basically scales with this TCH over TG, which kind of measures how much you heat the outflow with respect to the escape velocity from the companion. So if the companion has a weaker gravity, TG is lower, so you'll have a stronger M dot, as you would expect. And if you hit the pulsar more, then TH and also P naught will be larger, so you also get more M dot. So that's just a bit of intuition. Okay, so anyway, now we have this equation for the evaporation time. So now let's try to apply it to the observations, the sample that we saw in the table a few slides ago. Okay, so these are the results. So this is, yeah, so each point here is a black widow system. It's a millisecond pulsar orbited by a low mass companion. And what we plot here is the companion's mass. You see it's typically a few percent the mass of the sun. And we also plot the companion's period. You see it's several hours. And for each system, we also know P and P dot of the pulsar. So we know the pulsar's spin down power. And from the Fermi satellite, we know more or less how much of the spin down power goes into gamma rays, which can actually cause this evaporation, evaporate the wind. So for each system, we can now assign a gamma ray luminosity L gamma. We know the companion's mass, and we know the companion's orbital period. So we just plug them in the equation, and now we have an evaporation time scale, which is what we color code over here. So these are the results, and now let's examine them. So let's start with this point over here. So this is the original 1988 Black Widow. And you can see by its brownish color that this Black Widow evaporates its companion on a few gigayear time scale. So this kind of makes sense that we observe the system as it is and its current mass. But now let's see what happens to all the other systems. And what you see is basically a mess. So you can see that some systems, this black one, the dark brown ones, maybe even this dark red one, also evaporate their companions on a few gigayear time scale. But actually most systems, like this white one, all the yellow ones, and even the orange ones, you can see by the color that these take actually longer than a Hubble time to evaporate their companions, tens or even hundreds of gigayears. So it doesn't seem plausible that evaporation by itself could have evaporated these systems to the current mass at which we observe them. And the reason that we get such a large scatter, these very different colors, these 3 orders of magnitude in evaporation times, is if you remember from the table, then the Black Widow systems were similar, except for the pulsar's spin down power. The spin down powers were rather different, and the spin down power comes in the 4/3 power over here. So that's why it causes the large scatter with different evaporation time scale. And this scatter actually kind of makes it hard to kind of collect our results. So let's say we want to maybe collect our results by introducing some fudge factor, because maybe we forgot some order unity coefficient, we got some efficiency wrong. So if you want to introduce some fudge factor, we would have to, you see that we have to introduce a factor of about 50 to get the longest time scales to be shorter than the Hubble time. And if you now apply this factor of 50 to the whole population, you would also apply it to these kind of short-lived systems, which would now become extremely short-lived. So now with this fudge factor, the fact that you observe this extremely short-lived system would have meant that you should have also observed a much larger population of isolated millisecond pulsars that have completely evaporated their companions because they had several gigayears to do so. So we actually do observe some isolated millisecond pulsars, but the numbers are actually comparable to the number of Black Widows. They don't vastly outnumber them. So what I'm trying to say is that such a fudge factor wouldn't work. It wouldn't make sense when you add in the population of isolated millisecond pulsars. So our conclusion was that the evaporation story doesn't seem to work. It can't really explain the whole population of observed Black Widows. So what can work?
Just to check that I understand.
Yes.
So the model is that you start from a main sequence star, right? Roughly, give or take. And then the evaporation causes it to become a 10 to the minus 2 solar masses star, right?
Yes, so it's a bit more tricky. Yes, so actually, as you might notice from this, so this equation kind of gives you only the evaporation time at the current mass.
Right. So but the initial mass was about 100 times larger than that.
Yeah, right. So what I'm trying to say,
several e-folding to get there. So you actually need another factor of a few to get to that. So the actual, so if you started from a main sequence star, give or take, then you should end up with, you know, multiplying that by a factor of about 10-ish or so.
Yes. So exactly. So Asaf, so what Asaf is trying to say is that the problem is even worse. So this is the evaporation timescale given for the low mass that we observe now, a few percent the mass of the sun. If you plug in here a main sequence star, which is where you're supposed to start from, the problem gets even worse. Now the evaporation timescales will be even larger. So that's true. The problem gets even worse, but actually the scenario is a bit more complicated. So kind of the scenario is that you lose part of your mass in a Rostov overflow initially. And why would you be in a Rostov overflow? So for example, you can be pushed into Rostov overflow by gravitational waves. The systems are very close. But the thing is that gravitational waves depend on the mass. So when the mass of the companion gets low enough, gravitational waves become increasingly slower. So yeah, so actually you shouldn't plug here a 1 solar mass. You should plug here maybe a 0.1 solar mass. This is when gravitational waves become too weak. But still, the point remains, the problem is even worse. So this is kind of, even in the easiest case of taking the current low mass, the evaporation times are already too long, and they would get worse if you need to start from a higher mass. Okay, so what can work? So one idea that we're investigating right now is magnetic braking. So we have our pulsar. It emits some wind of the companion, but this wind, as we've seen, is generally too weak. It doesn't significantly reduce the mass of the companion. But if the companion itself has a magnetic field B, then it forces the wind to co-rotate with it up to what's called the Alfvén radius RA. So it forces the wind to co-rotate with itself, with the magnetic field, and with the companion to this radius. And because this Alfvén radius can sometimes be fairly large, depending on the magnetic field, it means that even a weak wind, even a small m dot, can carry a lot of angular momentum because it carries it to a large radius RA. So even a weak winds can significantly spin down the companion, but because the companion is so close to the pulsar, its spin is tightly locked to its orbit. So when you spin down the companion, what you actually do, you take out orbital angular momentum. So similarly to gravitational waves, which we just mentioned, or to tides, maybe a closer example, you can kind of take angular momentum and push the companion towards the system. You can push it towards the pulsar, you can push it towards Rostov overflow, and you can then force and keep it in stable Rostov overflow. And then the companion can lose much more mass in the Rostov overflow than in the initial wind itself. So this magnetic braking through this process act as a magnifier of the mass loss rate from the wind. And the reason that we kind of find this solution appealing is that the Alfvén radius is inversely proportional to m dot, to the wind. So the stronger the wind, the more mass the wind carries. Actually, it's harder for the magnetic field to force it to co-rotate with it to a large radius. So the Alfvén radius becomes smaller. So when you go to J dot, to the angular momentum loss rate, you can see that there are these competing effects. So on the one hand, a stronger wind carries more mass, but it carries it to a smaller distance, RA. And you can see that these competing effects, just by summing the power laws, they nearly cancel out. So at the end, J dot, the magnetic loss rate, goes like m dot, the mass loss rate, to the 1/3. So this magnetic braking is not only an amplifier of the wind, it also doesn't care too much about the initial strength of the wind. So even very different winds will still magnetically evolve more or less on the same time scale. So the reason we found this appealing is if we go back to this plot, so the left panel is the same plot we had before. These are the evaporation time scales. And you can see that there are these very different colors. But now when you take the same systems with the same winds, but now you calculate the magnetic braking time scale, assuming some magnetic field B of 70 Gauss, which we'll talk about later. So what do you see? So now these are the magnetic evolution time scales. So first you see that all the colors are darker. Now all the colors are around 10 gigahertz. But more importantly than that, you can see that all the colors are similar. All the systems now evolve more or less on the same time scale. And the reason is this 1/3 power that kind of squeezes this large 3 orders of magnitude scattering evaporation times into a much smaller scatter of magnetic times. And this kind of uniform evolution timescales makes much more sense for the population as a whole. And the 70 Gauss, it was just chosen ad hoc to give a median magnetic evolution timescales of 10 gigayears. So you can kind of reverse the argument and say that if you would like to explain these systems with magnetic braking, then you must have magnetic fields on the order of 70 or 100 Gauss. Okay, so that's the basic idea. And now we're trying to kind of investigate it more thoroughly using the MESA stellar evolution code. And this code, what it does, it allows us to kind of, so up until now, we just solved, following Asaf's question, we just solved the condition at the current mass, a few percent the mass of the sun. But with MESA, we actually now evolve the systems starting from a 1 solar mass main sequence star, going all the way down 2 orders of magnitude to Black Widow masses. And apart from that, there are 2 important features that we incorporate in these MESA calculations. So one is that the magnetic field is no longer this ad hoc 3 parameter that we set as we wish to get the time scale that we want. So magnetic fields in these objects are generated by convection. So you can actually relate the strength of magnetic field B to the convective luminosity. And that's what we do here. We actually calculate and change B of the companion as we go along these tracks. And the second feature is that we change the boundary conditions of the companion to account for the pulsar's radiation. So the pulsar's radiation, apart from watching the wind, it also changes the thermal structure of the companion's atmosphere, which then affects its luminosity. And this luminosity determines how you travel along these tracks. So we incorporate all of this, and you can see that we are able to get kind of more or less consistent tracks that seem to explain most of the observations, but this is still preliminary work, so I won't talk about this more. Maybe if I actually visit in person one day, then I can say more about this ongoing work. Okay, so I'll summarize the talk, and then I hope we have some time for more questions. So the question was, can the evaporation scenario explain the population of observed black widows? And the answer is probably not on its own. The timescales seem to be way too long in some cases, and the scatter between the timescales is too large to make any sense when you add the other pulsar populations. But when this evaporative wind couples to the companion's magnetic field and drives magnetic braking, then it seems much more reasonable. Timescales now do make more sense, so we think it's a good way forward. And before I finish, maybe going back to Asaf's question, so if you remember this equation for the evaporation timescale and how it scales with the mass, so when you calculate the magnetic braking timescale, then you get a different equation, and this equation goes like m to this very low power. So now you can actually, it actually doesn't matter too much the mass from which you begin. The magnetic braking timescale doesn't change too much with mass. It's of course a bit more tricky because the orbital period and the B also change as you go along, but this is all accounted for in the MESA calculations. But just intuitively, you can see that now that depends on the mass is much weaker. So now you can actually start this process at a much higher mass. And this process alone can now bring a main sequence star down to low Black Widow masses. Okay, so with this, I will end and take any further questions. Thank you for listening.
Okay, I have a couple of questions. One, this effect on magnetic braking, can we measure that in the lifetime of the pulsar, or have estimates of the lifetime pulsar? For the crab pulsar, we have an estimate of 1,000 years lifetime, and we can compare that to magnetic braking, or I guess to the Larmor braking. How does this mechanism affect the lifetime of the pulsar?
Yeah, so the crab pulsar is much younger, right? I think it's yeah, as you said, it's 1,000 years old. Yeah, so you can't, Yeah, so basically what you're suggesting is to measure the change in the orbital period of the companion, right?
No, of the pulsar. Why would the companion period change?
So why would the pulsar change due to this magnetic braking? Oh, because you transfer material to the pulsar? Is that the... Okay, so yes. Yes, so actually, so the thing is, we do think that the pulsar spins up initially due to similar transfer of material, but that's in the earlier stages when you transfer more mass. So when the companion is massive and the companion is a solar mass, then m dot is also fairly large, and then you can significantly spin up the pulsar. But at this point, the companion mass is a few percent the mass of the sun. So the m dot, how much mass you add to the pulsar, even if you add mass to the pulsar, then it's negligible. You don't really spin up the pulsar anymore. But it's even worse than that because we actually think that actually this mass no longer goes to the pulsar. So the thing is that once the pulsar spins at millisecond periods, it actually can't really accept this mass. So the mass kind of comes, and then what happens is it's usually called the propeller mechanism. Basically, you have this pulsar with a very strong magnetic field and a very strong wind of its own, kind of spins very fast and just ejects this wind. So this wind doesn't really go to spin up the pulsar. It can, so since you have a propeller mechanism, you might imagine that this propeller might spin down the pulsar because we actually now take rotational energy from the pulsar and give it to the ejected material from the system. But still, the m dots are so low that they're negligible compared to the moment of inertia of the pulsar itself. At this stage, when you're at higher mass, then, yeah, then it can happen.
Yeah, I would be worried actually about the opposite thing. I mean, you put a magnetic field of roughly 70 Gauss, and you show that the time scale is comparable to the time scale that you're actually expecting to see. But I would expect actually that there would be a large diversity of the magnetic fields values for the companions, which could extend over several orders of magnitude. Like, even in our own sun, when you have sunspots, then the magnetic fields can be like 3 orders of magnitude above the regular magnetic field. So in fact, I would expect that the diversity in the times would be much larger than what you're actually seeing.
Yeah, so
point? That's a very large dispersion in the lifetime of these companions.
Yeah, so I think regarding the sun, so first of all, what we need here is so in star spots, there's a big difference between the local magnetic field. So if you have a small spot, the field in the spot will be very different than the field outside the spot. But the overall magnetic dipole of the sun doesn't change on 3 orders of magnitude. The sun has more or less the same 1 Gauss it has. It doesn't change too much. So maybe to answer the question more thoroughly, so we don't understand too much about magnetic fields, but what we do think we understand is that the magnetic fields in the sun are generated in different mechanisms than magnetic fields in these smaller, fully convective objects. So in the sun, what people think is that the magnetic field is generated at what's called the tachocline. That's kind of the border between the radiative region in the interior of the sun and the outer convective envelope. There's strong shear in this radiative convective boundary, and that generates the magnetic fields. But that's for the sun. And these objects are very different because they rotate much faster. So the spin period is the same as the orbital period because they're tightly locked. So the sun spins once a month. This spin once every few hours. And they're also fully convective. So this kind of changes. It's a different magnetic field mechanism. So here we think that we know from observations of similar fully convective objects and measurements of the magnetic fields that there is some scatter of magnetic fields, but there's a relatively well-defined relation that given the convective luminosity, how much heat you have to extract from the object, the magnetic field is more or less given by up to a factor of a few from this relation. And since all these objects have more or less the same mass, and since in this regime, the magnetic field doesn't depend too much on your spin, we expect that just by having the same mass, they should have relatively similar magnetic fields. So that's our expectation.
well, not if they started from different, well, if they have different initial conditions, right? Because you're talking now about kind of the outcome, right? After they have lost already a lot of their mass, right?
Yeah, so the thing is that, again, if you kind of, if you want to compare the field from, let's say, some flux freezing because you started from a larger radius, this will be much smaller than the magnetic field that actually will be generated by the convection itself of these bodies. So we think that these bodies actually forget their initial conditions because if you take, I don't know, if you take Jupiter, for example, then its convective luminosity doesn't care about its initial condition. It's now cooling as if it's cooled from infinitely hot conditions long ago. And since it's cooling, we think it's coupled to its magnetic field generation through this convective luminosity. We think that you don't depend too much on the initial conditions. Like if all you have to know is the internal luminosity of the body, then the internal luminosity doesn't care about the initial conditions.
Okay, okay, accept that. All right.
Any other questions? Going once, going twice. Okay. If not, let us thank Sivan again.
Thank you all for coming and listening.
Well, thank you very much.
If anyone wants to stay on and discuss freely, feel free to do so. I'm stopping the recording, so you should feel free.